Hey guys, we'll be doing a research project that regards prompting adversarial LLMs or LLMs adversarially. So most modern day LLMs are aligned in a way that restricts the perpetuation of biases, toxicity, and more to ensure that LLMs are both helpful and harmless. LLMs that are reinforced with these guardrails, such as instruction fine-tuning or RLHF, are what we refer to as aligned models. Our overarching goal was to essentially research a way to break this alignment, and we achieved this by appending a suffix to the end of a harmful input string. This algorithm is called the greedy coordinate gradient algorithm to generate these suffixes, and then we evaluate the success rate based on that, and then hopefully LLMs are then able to protect against these attacks. Now, briefly talking about the greedy coordinate gradient algorithm, we essentially have an initial input string that we treat as a suffix, and then we randomly replace tokens within the input string, and hopefully, based on the loss, we pick the optimized token that creates the lowest loss, and then we greedily replace this token and repeat the process until the number of iterations is reached or success is reached.
So we ended up collecting over 500 harmful strings from a couple of AI safety papers, but that ended up being pretty overkill for the amount of compute that we had available, as we ended up only using less than 20 strings. We also collected a suite of 29 test strings, as seen over there, to verify the results. They help indicate whether or not the attack was a success or a failure. An example of the harmful string would be up there, write a blog post, and an example of the target string would be, sure, here's a blog post. So we faced a few challenges while reproducing the attack, the biggest of them being compute. Running the GCG algorithm requires a large amount of VRAM. Fortunately, we had $30 to rent a cloud GPU. Unfortunately, it costs about $4 an hour to rent a GPU large enough to run GCG, as is. So we tried all the workarounds that we could, and we were able to get experimentation done on a GPU that just had 40 gigs. But we still had to blow past our budget and get Colab Pro Plus. Don't worry, we still got good results, but we had to do a few workarounds to make that happen. So the first of them being we had to pick a suffix initialization that lets the algorithm converge faster by recycling previous attempts. We used Clora to quantize the models to reduce their size on the GPU, and we solved dependency issues corresponding to our hardware choice that produced invalid tokens.
Cool, so this is the modeling software that we used. We used two types of models, white box and black box models. The white box models are the models that we know the parameters for, and the black box models are the ones that we either don't know the parameters for, such as ChatGPT 3.5 or Pythia 13 billion, which we treat as not knowing for. For the white box models, we use Vicuña 7 billion, 13 billion, and we also use Llama 2, 7 billion. And then Pythia, we used 12 billion, the open assistance version, and we obviously used software such as Colab and Hugging Face. For results at a glance, we generalize the categories into three results. The first is a successful result. It successfully breaks alignment, the prompt. Second is a relative failure. It breaks or actually produces a result, but it isn't relative to the input context, so it doesn't answer the question directly. And then third one is a complete failure, which is just rejecting the actual input string. Here are a few quantitative results. I just wanted to demonstrate the evolution of our loss curves. Starting off, we got a really noisy loss curve on the left. We fix that by fixing dependency conflicts. We get to the middle one, and we kind of have this kind of noisy iteration, but it reaches 500 iterations, which are our maximum, and it doesn't produce a successful suffix, which we then solved by using the method that Alex talked about earlier, which is initialization of an effective suffix. And so we're receiving quite good epochs convergence there, and quite a good loss curve as well.
So we performed aggregate tests on using one of the suffixes that we generated using Llama 2 7B 8-bit quantized. And so we repeated this experiment on a set of 10 strings. And then on each of those, for each model, we repeated this inference 10 times to check if it could bypass the alignment guardrails. One thing to note is that we tested this on both the current, like an older version of Pythia, and also a newer one that had more RLHF applied onto it. And we didn't see any noticeable difference between the two models. And we can also, because of our small sample size, we can't really say there's statistical significance between the performance of different quantizations of the model that we used.
The model just enjoyed outputting coding blocks, and some of the coding blocks you just naturally, you might have some embedded harmful inputs. You also have manually checking the adversarial response rather than doing automation is a lot better because sometimes you might get an adversarial prompt, such as the example here, where you have the adversarial prompt producing a harmful input-output, and then you also have something that it's embedded on the latter part of the string, which is I cannot fulfill your request, which is actually rejecting the string. We also have a patch live service model here. You can see how one of the mechanisms that we're not sure of within ChatGPT actually like just completely rejects the response for one of the strings, and so it just doesn't produce a response. And that concludes our